How'd the project go this summer?
Okay, I'll start off. So I'll start off with the problem. So as you can see in the abstract, there's two graphs, example graphs shown. And so we want to quantify how similar these two networks are. And it's very hard to tell just visually. And then even if you like map each vertex to the other vertex, it would just take too long exhaustively. In fact, it'd take n factorial combinations. So this would be way too exhaustive for like graphs, even for like 100 to like once you get into like n equals 1000, it won't even finish running. So that is our goal. We want to quantify the similarity in structure between two large networks. And so our solution is to compute the similarity score based on the number of trees in each graph. And so based on the counting of if both graphs have a similar count of trees, then they should be similar in structure because they contain those substructures. So yeah, so that's the statistic we want to come up with. But even counting these trees exhaustively takes O n to the k runtime complexity. So instead of directly counting tree sizes of size k, we compute the similarity statistics using a color coding algorithm, which Feifei will describe later. And so that is how we compute it in a much faster time. In fact, the runtime complexity is only O of n squared, and it provides a pretty good estimation of this tree count. And so we can use this for online social network applications, as we'll show later with our Facebook friendship network results. And we can also apply to bio applications such as protein networks, and as well as computer vision networks.
Okay, so now let's talk about the methods we used. So the first part is tree counting. So this is just when we want to count the repetitions of a tree in a given graph. So we use a color coding algorithm, which is significantly more time and memory efficient than the exhaustive search methods. So the first step of our tree counting algorithm is to randomly assign a color to each node in a given graph. And then we can center a graph by assigning weight values to the edges of the graph. And the centering process is supposed to help increase the accuracy of the counting. So you can get more accuracy with fewer iterations. The next step is then to partition the trees into smaller trees. And then using those tree partitions, you can use a bottom-up counting method to count successively larger trees. So for example, if you have a subtree within your larger tree of say size 2, you can count the larger tree first by counting the smaller tree, and then later on by looking for the counts of that smaller tree in a table, and then determining the repetitions of a larger tree based on the subtree counts. So you don't have to recount the trees every single time you look through the nodes. And this is really, really great because this dynamic programming approach drastically improves the time and memory efficiency of the algorithm. So it's very helpful. And just a reminder, we're counting colorful trees instead of any tree because the color counting algorithm is significantly more efficient. So the next part was to calculate the similarity score. So the first step of that is to find all non-isomorphic trees of a given size. And then for each of those trees, you can then count the trees in each of the graphs. And then you can take the dot product of the vectors containing those tree counts to get an unnormalized similarity score. The problem there is that the unnormalized similarity score will be significantly larger if the number of nodes and the number of edges are larger. Because it's just a dot product, then a higher number of edges will just lead to a higher similarity score. So that would be more reflective of the size of the graph than the actual similarity. So what we do is we divide the similarity score between two graphs by the similarity score between the graphs and them themselves. Specifically, we get divided by the square roots of those self-similarities. And that will return a number that is on a scale from 0 to 1, which is much more helpful because that actually reflects true similarity instead of just graph size. Another process we had was sampling. So we can sample a specific number of nodes from a given graph, and then from the node sample a certain number of edges. So then all the samplings would have the same size. And this is helpful because it would allow us to work with extremely, extremely large graphs. And also because we can account for some of the effects of different graph sizes by making sure that the final similarity algorithm runs on only same sized graphs. Yeah, and then once you have these samplings that are all the same size and number of edges, you can then calculate the similarity scores between pairs. For all of these methods, these were all coded in C++. We originally started with Python, but it was too slow. So we switched to C++ instead. And C++ is also great because Penn State University actually has a package called Fascia that includes a lot of the methods for tree counting already. So that was very much helpful. So we made edits to that and then built and added on our own methods to it. Another helpful tool that we used was the Duke compute cluster. At times we needed to submit very big job arrays to calculate, let's say, tree counts for like 98 universities or similarity scores between thousands of pairs of universities. So Duke compute cluster was really helpful for that. Yeah, so moving on to results. One good thing that we discovered was that our color coding algorithms and similarity algorithms both match quadratic time. So that is really good because that means that it should scale for significantly larger graphs and trees, and is significantly improved compared to exhaustive search.
Yeah, so I'll wrap up by talking about the rest of our results. So once we figured out that our algorithm scales efficiently, we needed to test to make sure that the results were accurate and reliable. So we did that by testing on correlated and independent Erdos-Renyi graphs. An Erdos-Renyi graph is when you have a fixed number of edges, often like 1,000, and then you have an edge probability P, and you have an edge between each node with, again, probability P. So then correlated Erdos-Renyi graphs, you subsample from that original graph with edge probability S. So you'll end up with two graphs that were sampled from the same original graph. And then independent is when you also subsample with edge probability S from an existing Erdos-Renyi graph, except the independent ones are separated from two different graphs. So naturally, you would expect the correlated ones to have a greater similarity score because, again, they are sampled from the original graph. And that's what we've actually visualized here. So we have different tree sizes from 3, 4, 5, 6, with 6 being our most reliable. And we really wanted to make sure that the results were separated because, again, the correlated similarity should be much higher than the independent similarity. And when we used k equals 6, we had the greatest reliability, and we saw that for these slightly higher tree sizes, our results were reliable. So that's exactly what we wanted to see, and that confirmed that we were ready to start testing our algorithm on actual networks from real life data sets instead of these simulations. So then one of the next things we did was we worked with some of the sampling that Feifei just mentioned. So we had 98 different Facebook networks that were data scraped from Facebook, and they represent friendship networks for different American universities. And the results that you see here are for two specific ones, MIT and UChicago. What we actually did was we subsampled 6,000 nodes from each of those networks, and then we subsampled 100,000 edges. And we did that twice for each network. And what we expected to see was that the subsamplings for MIT would have a greater, for MIT with MIT and UChicago, DChicago, would have a greater similarity than between the two universities. And again, that's exactly what we saw, which confirms that our algorithm is working correctly. And it's also important to note that because even though our algorithm is super efficient, some of these networks can still be incredibly, incredibly large. So it's still good to see that our algorithm is reliable when you take samples from networks instead of using the entire network. And then finally, we did a little bit of testing once we had the similarity scores between all 98 Facebook universities to see if we could try and find any patterns in that data and see how we could apply our code to come up with some sort of real world results. So what you see there on the top right is a heat map that shows different clusters that we created based upon the similarities between each university. So again, we ran a simple k-means clustering algorithm on all 98 universities. And what you see here is, again, a heat map where each individual square represents the similarity score between two universities. And you can see that our algorithm was efficient and effective in differentiating universities based upon similarity independent of size. So again, some universities have really high similarity, and those are the darker squares, and then some have very low similarity, closer to 0.2 rather than like 0.9. And that means our algorithm is working correctly and it is capable of differentiating between different networks. So then once we had those clusters, we also wanted to see if it was possible to sort of predict why certain universities were more similar in structure. So we looked at a bunch of different factors, including like in region, enrollment, what state the university was from, and none of those were really all that effective at predicting why certain universities were grouped together. The one factor that we did, or the two factors we found to be most influential, were the edge count and node count of two networks, which is what we have graphed here. So again, it's graphed node count on the x-axis, edge count on the y, and then the shading in that graph is actually our clustering from the k-means. And you can see that some clusters are more closely grouped together than others. For example, cluster 3 on that graph does have like most of its universities at the bottom, but it's not exactly a direct causation, and you can actually come up with a direct prediction. And that in the end is a good thing because if you could predict why universities would be more similar to each other based upon node count or edge count, then that would defeat the purpose for our algorithm. But because we can't do that, it really does affirm or reaffirm the need for this color coding and tree counting algorithm, because that is the best way to find the similarity in structure between two networks. And that's pretty much everything we accomplished this summer. I hope you guys enjoyed listening about it, and now we'd be happy to answer any questions that you might have.
This might be an easy question, but how many different colors do you use, and how many does it consider for a tree to be colorful?
So the number of colors is just the number of nodes in the tree that we're trying to count. So a colorful tree has like all unique colors. So it should have every single every single node should have a unique color.
So I talked to a number of other teams today, and most of them had to spend about 2 or 3 weeks just cleaning up what they had to work with before they could actually work with it.
How was your team's experience with getting everything ready and actually being able to execute what you wanted to do with it?
I can speak a little bit to the nature of the Facebook data if Louis or Feifei wants to talk about actually writing the code and cleaning that up. But the Facebook data we got was honestly pretty simple in format to convert. It was originally given to us in .mat files, which is pretty easy to convert to a CSV. And then the way that the C++ code needed to intake that data was in the form of an edge list. So what we needed to do was count the total number of edges and count the total number of nodes and have those at the top of the .txt file, and then have a list of all the edges between every single node after that. And that conversion was also pretty simple. So the Facebook data was honestly pretty easy to work with. I think a lot more of our challenges came from writing the code and then also optimizing it, which Louis and Feifei can speak to.
Yeah, exactly that. Because the Facebook data was just binary, so it was just whether or not there was an edge. And also, it's just like there is an edge between two students if they are friends on Facebook. It's not like a super complicated sort of thing. So that was pretty simple. Yeah, the challenges was more just like trying to avoid errors in our code. Yeah, in C++, it's very easy to mess up one thing and have the entire code not compile. So that was more of the challenge than anything.
Great. Are there, did you guys work or talk with any of the other teams about what they were working on in order to help yourselves figure out your project more? Or were you pretty much on your own? Or
I think we definitely were mostly on our own for this one. We definitely like worked very well together, but I feel like it was a pretty self-contained problem, if that makes sense. It was very theoretical, and the applications were pretty much intended for the data that we had. So I don't know how much of what we were doing would have been generalizable beyond the problem that we had at hand.
yeah, yeah.
Because yeah, I know that like the first week or week and a half was just understanding the algorithm conceptually, and like getting a background and lesson in like graph theory and trees and how you find isomorphisms and automorphisms, which again is very specific to the theory and the algorithm that we had at hand. So yeah.
I have a question for the project manager, Sophie. How is this going to affect or help enhance your understanding and work?
Or is it, do you feel?
Sorry, can you repeat your questions?
As far as the research and work that was done on this project, does that have any continuance for you in terms of your own work and research going forward?
It was a past work we've done on this graph similarity stuff.
Mm-hmm.
So we came up this algorithm and given two random graphs and how we can measure their similarities. So this project is mainly based on our previous theoretical result, and then we write out this algorithms in C++ and then implement this algorithm on this Facebook datasets and also do the simulations to test the performance of our algorithm.
Mm-hmm. Great.
Yeah. Sorry.
Go ahead.
Yeah, I think it's I think the students are really amazing in both codings and also their understandabilities of this series, and also they work really hard during the summer, and we meet every day from Monday to Friday. So, and I think we're a really good team, and we did a great job.
I can also speak on like what we hope to do in the future. Like we did mostly like we only applied it to one application, but there's plenty more applications we haven't explored yet. But to be fair, like most of our summer we worked on just like building the algorithm, like testing the similarity algorithm. And so and we also hope to like eventually create a website to like put all our visualizations on there, and also like all the package to explore and make sure the commands are all clear, since there's a lot of commands in our package that needs instructions. So yeah, we hope to get that up in the next few weeks.
Great. Please do send me a link. And also, please do send me your poster also, because we'll print that out and hang it up in our space this year. Yeah. So does anybody else have any other questions?